Today we're going to talk about first Pourbaix diagrams or potential pH diagrams. This is a pretty useful application of electrochemical thermodynamics that you'll find all over the place in electrochemistry, electrocatalysis, corrosion science, material science. Many of you have probably seen these, geochemistry. And then after that, we'll start on chapter 3, which is electrochemical kinetics. Okay, so does anybody know what a Pourbaix diagram is? It's a predominance area diagram. So it tells you the predominant species, not the only species, but the predominant diagram as a function of potential, usually versus SAG, doesn't have to be, and pH. And it was popularized by Marcel Pourbaix. I think it was his thesis work or something like that, in 1938. So sort of in the dawn of modern electrochemistry at TU Delft in the Netherlands. Okay, so we can think about this. It's kind of like a phase diagram in thermodynamics. A phase diagram tells you what thermodynamically stable phase is there. But it's not quite a phase diagram because, in fact, it reports on equilibrium. And it is only reporting the predominant species. Let's do an example. So I plot this. P, this is the potential in volts versus the standard hydrogen electrode. And this is pH. And I want a Pourbaix diagram for sodium, for example. Sodium metal. The first thing I always want to know on a Pourbaix diagram, these are for aqueous solutions, by the way, which, is related to the fact that we're looking as a function of pH. You have pH in non-aqueous solution, but it's a little bit more challenging to define. So we want to know what does water do as a function of pH and potential. That's the first thing we always use as our reference reactions in a Pourbaix diagram, because that's the reactions of the solvent. So what are the two reactions that water can do if you add electrons to water or you take electrons away? Okay, if you can dissociate it, so you can do this, and that's an equilibrium reaction, right? That's, the autodissociation of water. What about redox reactions that water can do involving electrons? You can make hydrogen from water, you can make oxygen from water, right? So the two reactions, right, are 2H plus 2 electrons goes to H2. This has an E naught of equal to what? Okay, yeah. Depends what our reference is, right? Yeah. Depends on the reference. So it's 0 versus standard hydrogen electrode, right? Good, okay. This is 0 versus NHE or SHE. So we can plot that here. What pH? What pH is this?
Yeah, pH 0.
Why is it pH 0, Liam?
Standard state definition, right?
Okay, so at standard state, it says, what's the definition of standard state? Just tell us all explicitly. Well, in this context?
Yeah, it's a unit activity acid.
Unit activity acid with about 1 molar, which is about pH 0, right? So we can go to pH 0, and we can actually plot now at 0 that reaction, right? So that's going to be the potential where this reaction is in equilibrium, right? So example, if I have a platinum electrode in water and I have hydrogen at 1 atmosphere and protons at unit activity, it will be in equilibrium with that solution at pH 0 at 0 potential versus standard hydrogen. It's just the definition of the standard hydrogen electrode, right? Okay, that's easy. How does this potential change with pH? The Nernst equation, exactly. It's the Nernst equation. Okay, so let's get the pH dependence of that reaction. So how do we do that? So delta G equals negative NFE. Delta G equals negative NFE, that's easy. We know that, it's just the definition of free energy and potential, right? And then we know that that's equal to RT ln Q plus delta G naught, right? And so we can write the Nernst equation, E equals E naught minus the sign right, RT over NF ln Q. So that's just plugging these things in there. Delta G naught equals negative NF E naught by definition. So that's easy. So what's Q here? Product over reactants. So AH2 over AH plus squared, right? Pretty straightforward. What's the activity of H plus? Well, we're going to define the activity of H plus equal to 1 if pH2 equals 1 atmosphere or 1 bar. That's what our standard state. So we're actually just defining that. And we can define the standard state wherever we want, but this makes it very convenient to define it at 1 atmosphere. So that goes to 1. What's N? 2, right? It's a 2-electron reaction. Just so you see it explicitly, it's easy, but let's work it out. E naught minus RT over NF ln A, well, AH2 is 1, so I can write this as AH plus to the negative 2, right? And this is 2 here. Okay, so I can take that out, the log term. It cancels out the negative 2 on bottom. So I get E naught minus RT over NF over F, right? ln activity H plus. And so this is the pH dependence now, but it's written in terms of activity of H plus instead of in terms of pH.
I guess it's plus.
Plus, yep, we lost the plus, good. And does that make sense? Because as the pH goes up, right, is it going to be, so it needs to be, yes, that's right. So this is going to be negative here. So as the concentration goes up, it's more positive, it's easier to reduce. So that's right. So as this goes down, as the pH goes up, the activity goes down, then this term becomes more negative, it's harder to make hydrogen. So we got the sign right, that's good. I'll also check that just on our intuition. So we need to convert this into pH. So if we take we let AH plus is basically concentration of H plus. If we take our reference state to be 1 molar, and we assume activity effects are negligible, and the other thing we need is ln of x equals 2.3 log x. So we need those two things. And then we get quite straightforwardly that E equals E naught plus RT over F times 2.3 times log H plus, and pH equals negative log H plus concentration. So we have E naught minus 0.059 volts times pH. So these prefactors at room temperature, this is 0.059 or 59 millivolts. Okay, so that's the slope. So the slope of the line is 59 millivolts per pH unit. So we call that's a Nernst. Anything that changes in a 59 millivolts per order of 10 per order of magnitude change in some species, we call that Nernstian. It's a Nernstian pH response, okay? And that's just because these free factors, 2.3 RTO ref is 59 millivolts of room temperature. Okay, so what does this look like? What's it at pH 14? 59 millivolts times what? Times 14 is negative, so this is going to be negative 0.8, and it's actually 830. And so I can just draw a line here. And this is basically the H plus H2 equilibrium, right? And in fact, if you look in Barden-Faulkner, this reaction is exactly the standard potential. So this is going to get a little confusing, so pay attention. So if I take 2H2O plus 2 electrons goes to 2OH minus plus H2, E naught equals negative 0.83 volts versus SHE. Okay? So what's different between this reaction and this reaction? pH is different, right? So they're the same reaction, right? Like I could add 2 OH minuses to both sides of this equation and get that one, right? You see that? So they're the same reaction. It's just this is happening in pH 14, this is happening in pH 0 at standard state. Remember, standard state is 1 molar of everything. So by definition, standard state is pH 0, because I have protons are in this reaction. And by definition, standard state is pH 14, because I have hydroxide written in this reaction. They're actually the same reaction. They just have different standard state potentials because I wrote them different. It's purely the notation and how we define the notation. Of course, physically, we think about these reactions differently. In one case, you have a lot of protons, so the microscopic mechanism could be different in dragging hydrogen, making hydrogen an acid, and making hydrogen a base, where you don't have any free protons. Okay, but thermodynamically, they're the same reaction. They just have different standard potentials because we define standard state differently. Make sense? So you can look up this in Barden-Faulkner, you can look up this in Barden-Faulkner, whatever. Now, what about the other reaction? For water, what's the other reaction that can happen in water?
Oxygen.
Oxygen evolution. So what reaction is that? Let's write it in acid. Tell it to me. We have to take water, right? Okay, let's put the 4 electrons on the other side. Plus 4 protons plus O2. There we go.
Yeah.
So what's E naught for this?
Negative 1.229.
Okay, so we'll be a little bit sloppier. Plus 1.23 volts versus what?
SH.
Versus SHE. So I could put another, I would make that 1, and then I can put another dot here. Another dot, which is going to be the oxygen evolution reaction OER and acid, right? Now, could you calculate the pH dependence of this? Based on what we did? Do you think it's going to be the same pH dependence? So think about the overall reaction. Going from water to make oxygen and hydrogen. Do you think it depends what pH you're at for this reaction? Does delta G depend on pH? No. So this actually has to have the same pH dependent. Otherwise, delta G, E right minus E left, right, would be pH dependent. That can't be. Because there's no protons in this balanced chemical equation. And in fact, what you see here is anytime there's an equal number of electrons and protons transferred in the reaction, this is the exponent that it's raised to, its activity is raised to in the log term. This is the prefactor N, they cancel.
Yeah.
So you'll see that. We'll go through that again. So okay, we can just draw this line. And likewise, I could have looked this value up to pH 14. I could have written the reaction in base, right? I could have written 4OH minus goes to O2 plus 4 electrons plus H2, H2O. Okay, I could have written that out. I could look that up, and I would have found its potential is 0.4 volts versus standard hydrogen electrode. So the difference is always 1.23, right? So if you don't see that, you can spend some time with the equations and prove it to yourself, because it's a very important concept. Okay, so this is our our blank sheet for a Pourbaix diagram. This is what all Pourbaix diagrams have on them to start with. And then we care about, what do ions, metals, how do they react in these situations? And so we need a way to figure that out. So if I have, sodium. I want to do a very simple reaction of sodium. How do I do this on this Pourbaix diagram? What happens when you put sodium in water? First, you make hydrogen, it reacts with water. So what's the redox reaction of sodium? Sodium, what's the reduction reaction that's going on? Half reaction. What's the reduction half reaction for sodium? Okay, so I could do 2H plus 2 electrons goes to H2, right? That could be a half reaction. If I put sodium metal in water, in acid, that would happen. What happens to sodium? What's the half reaction for sodium? What's that? Loses electrons. So if I want to write that as a reduction reaction, right? So it's going this way, but written as a reduction reaction, right? It's sodium plus an electron goes, sodium cation plus an electron goes to sodium solid or metal. And what's E naught for this? Do you think it's going to be negative, positive? What does your chemical intuition tell you? So the spontaneous reaction is Na plus 2H plus goes to 2Na plus H2. And this has some delta G, and this you can get an E, reaction, right? This reaction is spontaneous. Can you say this reaction is spontaneous or the reverse reaction is spontaneous? These are half reactions. Half reactions are not spontaneous or unspontaneous or whatever. They're just half reactions. You cannot get a delta G and figure out the spontaneous unless you know what the overall reaction is. It's a very important point. But we can divide an E naught. And remember, the E naught is really telling us, and that's getting back to what you said, it's telling us the driving force for the reaction when you couple it to a standard reference half reaction. So this is going to be E naught versus SHE, right? And so if I'm coupling this reaction to SHE, so I'm actually taking the electrons from hydrogen to make sodium, driving this reaction backwards, that's pretty not spontaneous, right? So this is actually very negative, negative 2.71 volts versus the standard hydrogen electrode. Okay. So what this is telling you is this is a very strong reducing agent, right? This species will donate its electrons to a lot of things. Anything that has an E naught more positive than that, it will donate its electrons spontaneously. So we can plot that on this graph. Now, what is the pH dependence of this? Okay, what specifically about this half reaction makes it so it has no pH dependence?
There's no H plus.
No H plus in to put into Q, right? So remember, E equals E naught plus RT over MF, ln Q, the good old Nernst equation. What goes in Q? Products, activity of products over activity of reactants. So no protons, no pH dependence. So, gosh, I have to change your diagram here, sorry. Negative 2.7, pH, 0, 14. So E naught is going to be at 1 molar sodium plus, but that's not going to affect the pH. So I can put a dot here at negative 2.71, and there's no pH dependence. Okay, so it's just a line. This is in fact the Pourbaix diagram for sodium. It's the simplest possible Pourbaix diagram. You can have sodium plus, or you can have sodium metal, and you have to basically be under very reducing conditions one way to think about this is the electrochemical potential of the electron needs to be very, very negative, right? It's really unstable, okay? So that it's very reducing in order to take sodium plus and make sodium solid spontaneously. And what this tells you actually, you'll be able to practice this a little bit thinking about reactions. And this is a great thing for practicing for the midterm, because I always ask the question about Pourbaix diagrams and predicting reactions for Pourbaix diagrams, because it captures a lot of the aspects of thermodynamics I think are important. You can actually look at this and you can say, okay, well, if I'm going to drive a reaction, say going from sodium to sodium plus, I can drive that reaction that way. Okay, that's going to be an oxidation, right? I'm oxidizing the sodium to sodium plus. Those electrons have to go somewhere. So I have to drive another reaction the other way. And because this line is above that line, this is spontaneous. So it's spontaneous to drive protons H2 and Na to Na+. It's also spontaneous to drive protons H2 and O2 to H2O, right? But there's not very much O2 around in water, right? Just a little bit of dissolved O2, so you're primarily going to drive this reaction. So we'll have more chances to practice this. Are there any questions? If the line is above, the line that is above a line below, it'll be spontaneous to oxidize the thing below and reduce the thing above. Or another way to say this is this can oxidize this. So the higher thing can oxidize the lower thing. The lower thing can reduce the higher thing. And you can just see that from working out. It's just all the thermodynamics you guys have been working on, and the delta E's, and cell potentials, and spontaneity, but it's just on a diagram now. Okay? This is really useful in predicting stability of compounds under electrochemical conditions. We use it all the time in electrochemistry. This is an excellent question. Thank you for asking this. Okay, so this equation has H plus in it, doesn't it? So you're saying, it looks like it changes with pH.
It's like I could write a Q.
You can write a Q that changes with pH. Well, guess what? This distance changes with pH. So the half reaction doesn't change pH, but the delta G for the full reaction sure does, because it's the pH dependence of this reaction that's giving rise to the pH dependence of the overall reaction. So this is why it's really clear. And there's so much confusion among students and PhD students, and even in papers you read between what's a half reaction and the thermodynamics of the half reactions versus the full reactions and their various pH dependencies and activity dependencies. So you got to keep all this stuff straight and be really clear about what you're talking about. So let's do a harder one. Do aluminum. Label our plot here. Volts versus SHE. This is pH. Okay. And we're going to do it for aluminum now. So first of all, I can go right away and I can plot the reactions of water, right? We know how to do that. We figured that out. You should work out the pH dependence of the oxygen evolution reaction. I think it's actually in the homework. It's easy. We did it in class for hydrogen. And 14 is going to be negative 0.8 something. So there's going to be kind of a line here. And sorry, it won't be perfect here to scale, but I'll do my best. So there's water. This distance does not depend on pH, even though it looks like it does a little bit in the diagram. This is 1.23 volts, right, everywhere. Okay. And now I want aluminum. So I actually have to put on this diagram all of the relevant acid-base equilibria, right? So there's acid-base chemistry going on here, and redox chemistry, and coupled acid-base redox chemistry. Okay, so we're going to do that. It's not that hard, but it gets a little tedious if you're not used to it. And then you'll have the opportunity. When we do this, for now, we're just going to assume standard state, 1 molar for all species, right? For all soluble species. Okay, so we're going to assume that. Now, you have to specify that for any given Pourbaix diagram. If you might plot a Pourbaix diagram at 1 micromolar, or 1 millimolar, or 1 molar, the predominant species might change because the equilibrium might be adjusted. We're going to do standard state to make it simpler. So what are some reactions of aluminum that you might have? Redox reactions. What happens if you put aluminum metal into acid? Have you guys ever done this? Take aluminum turnings and put it into HCl? Dissolves and makes hydrogen. And so what's happening? The aluminum's oxidizing, so Al, and what are the two oxidation states that's going between? 3 plus, 3 valence electrons in aluminum, right? So aluminum 3 plus 3 electrons goes to aluminum salt, okay? And that has an E naught of negative 1.68 volts. By the way, what reacts more when you dump it in water? A piece of aluminum or a piece of sodium?
Sodium.
Can you tell that from the value of E naught? Which one was more negative? Sodium. So if you couple sodium with water to make hydrogen, it releases a lot more free energy than coupling aluminum, right? So we can put this, what's the pH dependence of this? What's the slope?
0.
0, no slope, no protons, right? So we can do this, 1.68. We can just pick a different color, make it a little cuter. Go. I could say aluminum down here, and this is going to be aluminum solid. And then I'm going to have aluminum 3 plus broadly up here, right? But if you know anything about aluminum chemistry, does aluminum exist as an aluminum 3 plus cation at all pHs? No, it doesn't. Aluminum is a Lewis acid and undergoes acid-base reactions with water as a function of pH. And so we need to understand all those equilibria to fill out the rest of this diagram. Now we know we're going to have aluminum 3 plus up here because that's governed by this equilibrium. We don't know what aluminum 3 plus species we're going to have. And so let's fill that out. But we'll leave this here temporarily as this reaction. Okay, reaction 1. Okay, so you have to know something about the acid-base chemistry in order to plot one of these diagrams. You can figure that out actually from thermochemical data. So if you had a table of all the aluminum species, right, you could actually calculate delta G's for any acid-base reaction. I have a very large book in my office by, it's edited by Al Bard, who's like one of the grandfathers of electrochemistry. And if anybody wants to see my signed Al Bard playing card, they can stop by as well. I'm serious, I have one. It's like a baseball card, but it's, for electrochemists. I'll bring it to class next time, I'll show you guys. Someday it's gonna be worth money. Okay, so what was I talking about? Equilibrium. So you need to know these things, so you can look up all these delta G's and you can calculate delta G's for any given reaction. So we need to know the species. So there's some species of aluminum. One of those species is aluminum hydroxide. Oops. And that's a solid. That's precipitate. So if you take aluminum 3 plus and you titrate it this way, you'll actually precipitate out aluminum hydroxide. Okay, so this is the thing you'll find in thermochemical tables. And then the other thing, if you keep increasing the pH, you'll form an aluminum hydroxide species, aluminate species. And this is aqueous, this is soluble. Okay. So it turns out aluminum 3 plus is really this. It's a hexaaqua aluminum species. So it's coordinated by 6 waters. Pretty much all cations are coordinated by water. You don't have the bare cation, right? It would be way too reactive with that high charge density, so the water dipole is oriented around it. And then as you increase pH, you increase hydroxide concentration, and you successively form species with more coordinated hydroxide ligands. And some of them are very complicated. You have a whole range of oxyhydroxides that form. So you generally find, as you go this way, you increase hydroxylation. So we need to know the reactions here. and we can write them out. You can calculate the thermodynamics from tables or from delta G values of formation. Here I'm just going to write the numbers. Okay, this has K equals 10 to the 10.2. So that's the equilibrium constant for this reaction. So what's the definition of the equilibrium constant again? So it's the equilibrium activities of the products, the product of the products over the product of the reactants, right? Raised to their stoichiometric coefficients. Okay, so we know that data. So I have to figure out how do I put that on here. And I want to basically find the pH where I go from having predominantly this species to predominantly this species. Right? I'm asking that question. Okay, so I can solve this pretty easy. I can say K, and I'm going to take concentrations instead of activities, because we're going to ignore activity coefficients for this purposes, though in Pourbaix diagrams you can include activity coefficients, that's fine. And the activity, or the constant, the effective concentration of aluminum hydroxide solid, its activity is what? 1, right? Because it's a solid phase. And then I have concentration of H plus to the third. That's what K, and that equals 10 to the 10.2. And I'm actually going to ask the position where this is at 1 molar is in equilibrium with this solid. Okay? And then if I go more basic than that, this solid is going to predominate as the species. Okay? So I'm going to ask where is the equilibrium when this is 1 molar? So I can solve this. Solve for Al3 plus concentration equals 1 molar and get concentration of H plus. You find that it equals 10 to the negative 10.2 over 3 equals 10 to the negative 3.4, or pH equals 3.4. So you can do the math, but it's basically just solving this equilibrium expression for what's the proton concentration when Al3 plus is 1 molar in equilibrium with aluminum hydroxide. And so we know at pH 3.4, there's going to be some sort of equilibrium here, right? And the fact that this line is straight up and down means that it's purely an acid-base equilibrium, right? It's the same at all potentials. The electrons are not involved in this equilibrium. So the other equilibria is AlOH 4 minus plus H plus goes to AlOH 3 plus H2O. By the way, these are like protonation constant, actually. These are not Kas, right? Because the Ka would be for the reverse reaction. If you know this is acting as an acid, then you would write the reaction in reverse. But this is how, I have a handout. I need to give you the handout, actually. Oh, I should have printed that out. I will post it on the webpage, and you can see the handout on Pourbaix diagrams. That's how they do it in this handout I'll give you. It's not in Barton-Faulkner. It's a pretty trivial extension of thermodynamics, but it's pretty practically useful. So K equals 10 to the 12.4. And you can go through the exact same thing, and you find that pH, where 1 molar AlOH 4 minus in equilibrium with AlOH 3 solid is 10 to 12.4. And you can see that this is a one proton transferred in this equilibrium. So then up here at 12.4, we're going to have AlOH 4 minus. Okay, but somehow, now we have this problem here, right? So we wrote this aluminum-aluminum 3 plus reaction, right? But it's only valid to here. Because once you get past here, you don't have predominantly aluminum 3 plus, you have predominantly this, aluminum hydroxide. And then once you get to basic conditions, you have this aluminate, soluble aluminate species. So we actually need to know these equilibria, right? Not this equilibrium. So this line, we're going to have to recalculate where this line is, right? Because that's not the relevant line in those conditions. Okay. So now we just have to do a little bit more math, and we'll just finish it up. Okay, so we can write a reaction for 3 electrons plus AlOH3 plus 3H plus goes to Al plus 3H2O. And we can calculate E naught for this reaction from delta G's. So if I wanted to calculate an E naught for this half reaction from delta G's, how would I do it? Okay, so you use delta G's of formation, right? You do this in the homework. Delta G's of formation for all the species, right?
Yeah.
So what's the delta G of formation of the electrons?
You should couple it with the hydrogen.
Okay, you have to couple it with another reaction. That's exactly right. So I have to basically say, okay, well, I'm going to couple it with 3 halves H2 goes to 3 electrons plus 3 protons. And if I couple it that way, I cancel out the electrons and the protons, and H2 is an element in standard state. So it has a delta G of formation of 0. So it turns out practically, if I do it this way, and I'm calculating versus the standard hydrogen electrode, I can just ignore the electrons and just do products minus reactants. Because, if I add this in, and the delta G of formation of protons at 1 molar is 0 also. So anyway, it just comes from the fact that we're coupling it to the standard hydrogen electrode. So anyway, so you'll go through this in your homework and in preparing for the midterm. So we can calculate E naught, delta G equals negative NFE. We can get negative 1.47 volts versus the hydrogen electrode. Does this have a pH dependence?
Yes.
Sure does, right? So E equals E naught plus RT over NF. Everybody can just calculate on your notes, actually. You know how to do it, right? Plug in LNQ, so just calculate it. I'll do it up here while you're doing it in your notes. So that Q is going to be products. So this is going to have activity equals 1 because it's the solvent. That's we're going to just in standard state we define that. 55 molar water is activity 1. Okay, standard state of the solvent. This is going to have activity equals 1. It's this is going to have activity H plus, right? And this is going to have activity equals 1, 2. So we define it that way, right? So what we get, products, looks like the signs are on. Yes, that's right. Thank you. Okay, so concentration of H plus to the 3rd power, and what's in? 3. Oh, that's convenient. Look at that. We have the cancellation again thing, right? So the negative 3, H plus the negative 3, cancels with the negative 3 there. And so that should just give us negative 1.47 volts minus 0.059 times pH. Right? Because we're just going to cancel, and we're just going to get the same exact thing we did for the hydrogen evolution reaction, 60 millivolts per decade. Okay, so let's go here. So we can go to our plot, and we can add that to our Pourbaix diagram. So we can go right here. So we know these things, right? These things meet at this point, right? And that's actually going to be the starting point for this line. Okay, so if I extrapolate it back, this would go to negative 1.47 at pH 0, but I know it has to go through that point because of the thermodynamics of the situation. So, and we know the slope. The slope's the same as the hydrogen evolution reaction. Okay, There we go. So now I have this region, right? I have this region, I have this region. And now I just need to do this region. Okay? So we need to do one more reaction. 3 electrons plus AlOH minus 4 plus 4H plus goes to Al plus 4H2O, and we can again calculate and do not for this, equals negative 1.23 volts. Okay, so I have this reaction. What's the pH dependence? Oh, it's not 0.059? Why not, Dakota?
Because you have a proton with 4 and electrons with.
Ah, okay, they don't cancel out, right? So if I write this equation again, E equals E naught minus RT over NF, ln products, unit activity, reactants. Now this is not, this is not necessarily going to be always a unit activity, but we're writing the Pourbaix diagram for all soluble species at unit activity. You would specify that, or the Pourbaix diagram would tell you what activity to take for the aluminum species. So we're just going to set this to 1. And we don't even worry about the activity of the electrons because it's sort of canceled out by referencing it to the hydrogen electron, right? And so I basically have, again, 1 over N. What was N again? 3. And H plus to the 4th. So that's going to be E naught minus 0.059. But now I have 4 over 3 times pH. There you go. And it's going to go from this point, and this is not very quantitative, but it's okay. It's just going to have a little bit steeper slope. This has no slope. There's no protons in the balanced chemical equation. This slope is given by this Nernst equation. Right? This is E. This is E. Well, B. This is E. E in units of volts versus SAG. So this is Y. And pH is X.
Okay.
And I've written proton concentration in pH. So this is Y equals mx plus B. So this is slope. And here the slope is steeper because of the non-equal proton to electron ratio in the balanced chemical. Okay, so let's let's do an example here. What happens if I take aluminum based on this diagram? I want you to use the diagram to predict reactions in aluminum in water. So I take a chunk of aluminum and I turn on the tap and I pour water into a beaker and I throw a chunk of aluminum into water. What happens based on this Pourbaix diagram? And why don't you take a few minutes to talk about it in your local environment and tell me what's going to happen and why. Okay, so what if you waited to time equals infinity? What would happen to that point?
The pH would change
Oh, the pH would change. Why is that?
because we're evolving hydrogen,
So you're consuming protons, the pH would get more basic.
and so then that would lead us more towards the aluminum.
So it kind of depends on how much aluminum you had, how much water you had, and if you waited infinity time, would you have any aluminum metal left? You have very little, because it's a very strong reducing agent. So if you think about the equilibrium, you could actually calculate how much aluminum you have left. But you have so much water around, right, that mostly it would oxidize the water. But as was pointed out by the very first group, usually people don't get this. This is a solid. So in practice, you have a piece of aluminum. I mean, we know we have aluminum all over the place. When it rains, does our aluminum combust into hydrogen? No, because aluminum is coated with aluminum hydroxide, or oxide. They anodize it, that's anodized aluminum, and that prevents that reaction from further happening. So that's called passivation. So this is the passivation regime. So what happens, I I didn't spell that right. But what happens if you put aluminum in strong acid? Does it passivate?
No.
No, it just dissolves, right? You make aluminum 3+, you make hydrogen, all the aluminum disappears. What happens if you do put aluminum in strong base?
Dissolve.
Dissolves. I did this experiment once on accident. I took a base bath in graduate school for etching glassware, cleaning glassware, and I wanted to get rid of it. And we had this big aluminum ether container. You know, ethers come in like aluminum because they handle pressure. I didn't think about it, and I just poured it in there. Put it in the waste cabinet. Exploded. Why? Because it etched the aluminum, made hydrogen, built up pressure, and exploded, and spewed base all over the inside of our waste cabinet. And I went and cleaned it up with big rubber gloves and felt really stupid.